This is Duke University.
So I'm going to talk a little bit about my lab's work. We focus on the general problems of mobility and manipulation, and I'll try to talk about what the challenges are and what kinds of techniques we bring to these problems in my lab. So just like Ty was saying, robotics is this really interdisciplinary field, and you can come at it from a number of different directions, different techniques that you apply to it, different perspectives and philosophies that you take with it, and different kinds of disciplines that you use to build interesting systems. And one of the things that I would like to kind of think about in my lab is that we bring to the table a bit of all of this. We were a very broad lab, and we try to do a lot of different things. We essentially try to build systems and understand what kinds of techniques are needed to make them work. So just as an example of one type of systems challenge that we were involved in several years ago was the DARPA Robotics challenge. This is a challenge to build a robot that can enter a dangerous and degraded human environment. The kind of idea was something like the Fukushima disaster, where you have some dangerous environment it was built by people, but now people can't go into it. Now you need to send a robot in it and do various interesting tasks, useful tasks to try to somehow fix things, for example. And so they proposed 8 tasks that were representative of some disaster scenarios, and they really tested a whole bunch of different capabilities that needed to be integrated onto a single system: mobility, dexterity, strength, and also useful operator interfaces. So one of the things that the challenge that we worked on, the task that we worked on, was ladder climbing. And so here's an example of the robot that we used. This is called the DRC Hubo. And we got the robot to very reliably climb the various ladders inside of our lab. Basically, there's a lot of things that are interesting about ladder climbing. One of the things that you notice about this robot is actually climbing the stairs backwards, so it's very unlike a person. And this is because its capabilities are very unlike people. It can actually spin its head 180 degrees, so it can look backwards. It also doesn't have the same flexibility in a person's hips that you would normally expect of a humanoid robot, but just because it's a robot, it's somewhat slightly different. So in any case, we developed a lot of different perception algorithms, planning algorithms, and so on. We also do a lot of testing. So just like Amazon needs to test their systems quite extensively, we also do a lot of testing as well. And so one of the important tools that we have is simulation testing. So we did test robustness of our capabilities, because we only had a couple of ladders in our lab, and we needed to test to see whether or not we'd be able to address any kind of ladder that DARPA would throw at us during the challenge. And we showed that we did a pretty good job of covering the space of possible ladders in simulation. And we were also able to test things like the robustness of our various controllers by throwing problems at our system and seeing how they respond. So what we ended up doing was dropping balls on the robot as it started to climb these simulated ladders. And so what we ended up doing was just dropping heavier and heavier balls onto it. And we found that it was working with 5-kilogram balls, 10-kilogram balls, and we tested with a 15-kilogram ball dropped on it, and you end up seeing something like this. So we thought that was a pretty good result, and so 15 kilograms while you're climbing a ladder seems like a pretty big disturbance, so we were satisfied with that sort of result. So one of the interesting things about working in the real world, so we were pretty satisfied with how we were able to climb ladders, and it was actually really exciting during this challenge. We were one of the first teams to actually try more than a single step of this ladder. And one of the things that we ended up getting this big crowd interested in watching the robot climb this ladder. And one thing that you notice here is that its hand actually kind of slipped off the ladder rung, and finally at the very last step, it ends up doing this. So this mistake was caused by various things that we couldn't take into consideration during simulation testing, during in-lab testing. For example, wind. It was actually really windy that day, and so every time that we tried to take a step, we would not end up exactly where we wanted to be, and sometimes the system would be able to control itself back to kind of a nice configuration, and sometimes it wouldn't. And my students were so excited when they were watching the robot. They were supposed to be watching to see whether or not it was doing every step the way that it should, and they were so excited at that point that they forgot to check whether the hand had made a solid grasp on that wrong. Nevertheless, we thought this was a pretty good result, and actually we had a mention in The Economist when they were talking about the DARPA Robotics Challenge. We got this blurb at the very end of their article that was something like, So perhaps nothing like humanoid robots gets us to think about our own humanity. When the little DRC Hubo robot climbed up to the top of the ladder and fell off, it reminded us of human hubris and how we are destined to fail when we try to achieve something. It's some kind of commentary on human nature that this got them to think of. But in any case, we're pretty interested. We're pretty happy with that. So after that project, I thought it was a little bit repetitive. You know, once you do one step of a ladder, you can basically do every step of a ladder. So we always try to push ourselves to doing more complicated, more interesting things, and basically push the envelope of the state of the art. So my next project after this was to work on next generation climbing robots, and so we got a generous grant from the National Science Foundation. We're working with Stanford, UC Santa Barbara, the Jet Propulsion Laboratory, and also a spin-off company called Robotics to take this robot, which is the Robosimian robot. It actually competed on a different team in the DARPA Robotics Challenge. And what we're going to try to do is allow it to climb vertical and extreme terrains, and actually a huge variety of terrains ranging from flat ground up to vertical terrains. So we wanted to be able to do things like the things that are depicted on the right, climbing rock faces, climbing possibly in arboreal environments, and also climbing in things like jungle gyms. Just as an illustration of how fundamental these capabilities are, this is actually a baby bear that's on a cliffside. Its mother had just basically gone off screen and just left it to try to figure out how to get up this cliff by itself. And so with a bit of stumbling and a bit of kind of experimentation, it's actually able to figure out, the first time it's ever seen a cliff, how to climb it. And so it's able to, finally get itself up to this kind of more flat area and then finally walk off screen. So we want to develop the same sort of capabilities in our robots. We want the robots to be able to invent from the very beginning how they should be attacking a given terrain. This is a video of my brother doing rock climbing, so this is a pretty challenging rock route. We basically wanted to develop the same kinds of capabilities on this Robosimian robot. So here's a depiction of what we want it to do. What we want to achieve after 3 years of this project is to have the robot be able to autonomously climb what's known as a 5-7 route. This is a Yosemite decimal system kind of grading for human rock climbing, which is a fairly challenging route for a first-timer, but for an experienced person, it's not too bad. So inside of our lab, we built a rock climbing wall. We also have a Robosimian robot. We've affixed hooks and also now a variety of sensors to it. Oops, let me go ahead and play those again. And we've started to do some 3D modeling of the terrain. The robot's going to sense the terrain. It's going to sense the terrain with 3D sensors, and it's going to autonomously figure out where the footsteps that it needs to that it should place are, and also what body movements it'll do. So far we've only gotten a couple of feet up on the wall, but we hope to make some further progress hopefully over the summer and coming through fall. We're also collaborating with Stanford University. They have these really interesting kind of designs based off of microspines, which are a bio-inspired sort of idea. So things like insects small creatures like insects will have little hairs that go into the tiny indentations into the in the surfaces that they crawl on. And basically, we're going to try to do that, but on an extreme scale for this project. So hopefully, with this palm, they have several hundreds of spines that are individually compliant to the shape of the terrain. And for certain types of rock surfaces, you can actually hold 60 kilograms of weight, of vertical weight, just using a small 4x4 inch palm. And so we're also applying this to kind of a hand design. So ultimately, we're going to have a spiky hand that we put on the robot, and hopefully it should be able to climb a huge variety of different rock surface types. So speaking of manipulation, so you could think about locomotion as essentially a manipulation problem where you're manipulating your body with contact with the terrain. Usually when we talk about manipulation of objects, we manipulate objects using our body. So they're essentially complementary problems. So for the last 3 years, I've been working on the Amazon Picking Challenge, which is another sort of related mobility and manipulation problem. Not so much mobility, but primarily manipulation. And I've been working with these teams, and it's a really exciting sort of challenge. We end up having teams basically work for 6 to 9 months, trying to put together a system to address these Amazon Picking Challenge competitions. So basically we have these sort of shelves that we need to grab objects off of. We need to identify the objects. We need to figure out how to grasp them. And there's a whole host of system integration challenges, and it's really fun, and students get really excited by it. And so this year we have, I believe, 17 students who are working on the Amazon Picking Challenge team, and some of them will go and compete in the actual competition in July. So another topic that involves a lot of manipulation that I'm working on is this telerobotic intelligent nursing assistant robot, or Treena. Basically, the idea of the robot is to have a mobile manipulator in which a human nurse can go and log onto it and then start working with a quarantine patient that might have some sort of infectious disease like Ebola, or maybe it's an immunocompromised patient that they don't want to infect with their own diseases. And so instead of going in physically into these environments and potentially exposing yourself to these dangerous pathogens, you instead could log on to the robot and let the robot do the nursing tasks instead of your own body, and so you don't put yourself at risk. So it's been a really interesting project. This has been funded by the NSF, and so we've been trying to develop the capabilities of performing human tasks with this robot, essentially as a surrogate for your own human body. So we've looked at certain, so the other interesting thing about nursing environments is that they're extremely unstructured. They're one of the most unstructured environments that actually I've ever had a robotics project in. There's so many different types of devices and objects and different configurations of hospital rooms that we just cannot predict what is going to be there. And so it's very hard to develop full autonomy for this sort of thing. So instead we're working with a shared control kind of system where the human nurse performs some aspects of the task and the robot tries to put in a little bit of intelligence onto its own execution of those tasks. So we've been looking at various clinical tasks that are typical of nursing environments, and we're trying to allow the robot to be able to accomplish those. We ran lots of testing in a simulated nursing environment along with the School of Nursing here. So we ran 26 different fundamental manipulation and communication tasks. So for example, food preparation, instrument preparation, etc., cleaning things, moving things around. We had a shared control system with collision avoidance where the human was basically using haptic devices to control the arms of the robot. We also had an expert operator, or basically we had our own pilot of the robot. These were not untrained nurses. But we were able to complete 19 out of 26 of these desired tasks. So let me go ahead and switch to a video of this. So these are all sped up. You can see that it can do things like arrange food trays to be brought to a patient. It can do things like bring the trays over. We had to do a little bit of manipulation of the tray so that the robot could grab it. But basically, you can go ahead and drive the robot around to be able to do a lot of these kinds of food serving tasks, both loading and unloading food trays. We also also are able to hand things over to patients who might be sick. You can see that it's a little bit kind of like those claw games in a fair where you kind of have to drive the claw around to go grab things. So it's actually it's quite a bit slower than doing this with your own body. Typically we find that the tasks are about 10 to 50 times slower than normal. So there's certainly quite a way to go. But at least with these tests, we have shown that it is feasible to do a lot of the general tasks that nurses do in these environments. And so we need to think about how we're going to help improve the speed of these robots, how we're going to improve the reliability of each of these tasks. But you can still see that it does quite a bit that you'd want from a nursing robot. Okay, so what we want to do with that project is basically, right now our current motivation is to try to partially automate some of these tasks. So it's less like I'm driving the robot's hand around and observing where it's moving and then trying to grab something and seeing whether it's grabbed it. But instead I want to kind of move towards more of a supervisory autonomy sort of approach where you do things like point and click on the object that you want to grasp, and then the robot will automatically grasp it. And so our hypothesis is that by adding more autonomy on the robot, we can actually make this human-robot team work better than just with a human alone. I have a lot of different projects in my lab, and we try to bring a few different sort of secrets to making projects successful. I just want to mention a few of those. We think in configuration space or state space. This is a really fundamental sort of mathematical modeling of how robots and systems operate. We work with motion planning and trajectory optimization quite extensively. We also work a lot with 3D RGBD sensors like the Microsoft Kinect and Intel RealSense. We also do a lot of machine learning and computer vision work to be able to perceive the environment. We do a lot of rapid prototyping when we're trying to develop new mechanical devices, and we also do extensive simulation and evaluation before testing things on robots. And let me just close out by saying that we've gotten a lot of use out of this physics simulator that's being developed and maintained by my lab. It's called CLAMPed. We've been using it for 6 years now, and it's been used in a variety of projects, not just by our lab, but other labs around the world. It's been able to simulate things like locomotion, manipulation, and a whole host of other kinds of interesting robotics problems. It has C++ and Python APIs. It's pretty straightforward to get into and start diving into, and so it's been really a huge benefit to my lab, and students who come in and work for me for a few months, they're still able to pick up on the simulator and get their own projects working. So if you're interested in looking at it, it's, if you can go to clampt.org, KLAMPT.org, you can see more videos and also get started with running with it. So I'd like to thank you for all your attention. I'd like to also thank my collaborators and students. And if you have any more, if you want to get more information, you can check out my website or the CLAMPed website as well. So thanks for your attention.